Hi, welcome back to video tutorials on AIOS. This is part 2 video, and in the first part we were discussing about AIOS block scaling and load testing, the strategies involved in it, and what all policies and metrics we were using. So this, as it is a part 2, I mean in the part 1 we were discussing with a mid-sized model where we took an Magistral Small 2506 model. This was a 23.6 billion parameters model, and the RAM usage was somewhere around 45 to 47 GB when this model is loaded in FP16. And at that time we were showing how the requests per second were calculated, and how the metrics were behaving, how the response times were behaving, and how many requests were sent. All those were shared in the video tutorial part 1. And in this video we want to showcase same thing with a smaller model. The purpose for choosing a smaller model is we can send a more requests per second. So when more requests are sent, how the platform behaves. So are there any issues with the platform or not? So that's the reason we want to show you a smaller model. So in this video tutorial we'll be showing a smaller model which is known as Qwen3 version 1.7B model, and the number of parameters are 1.7B, and disk space that this model will take is around somewhere around 3 to 3.5 GB. And when the model is loaded, it will take somewhere around 4.2 to 4.5 GB. And if you do with a tensor parallelism, right, like splitting a model splitting in a same GPU, this would consume somewhere around 7 GB, because when model is splitted, it will take more RAM. And the maximum number of token is 32k. So this is about your model, what model you have. You need to have those data with you, and to calculate its latencies. So one instance of Qwen3 1.7B model in one A100, it was taking somewhere around 1.5 to 1.6 seconds. And here we were, as batching was involved, so, and also we were taking 256 tokens as a maximum tokens. So 4 sequence was involved in a batch. uh, so whatever the numbers here is, right, it's because of the 4 sequence in a batch, and the maximum output of token is 256. And this is in one instance. So if I run 2 instances in a same GPU, then it will come somewhere around 2.9 to 3 seconds. So same experiment, if I do it in a L4 GPU with one instance, that would come somewhere around 4.4 to 4.5 seconds. And one other interesting thing is, whenever we run this one instance of A100 in one instance of this model in A100, the GPU utility was somewhere around 60 to 80%, and when we run 2 instances, it was almost 100%. So there is no point in increasing the number of instances in a same GPU. So we will restrict our experiment with maximum of 2 GPUs per 2 instances per GPU in A100. Whereas in L4, when we run one instance only, we were getting somewhere around 85 to 80 to 90, 95 utility. So there is no point in adding one more instance at all. So we restricted with our experiment with only one instance in L4. If I do a tensor parallelism, where is like one instance running in 2 A100s, so I was getting similar 1.5 to 1.7 seconds, which is the tensor parallel 2. But this pattern may not be same for all other models. Like say you have taken some Magistral model or something like that, so it may be different. So this data is only for Qwen3 1.7B model. Token generation. So one instance, when it is run on one A100, we were getting somewhere around 162 to 164 tokens per sequence. Since the sequence, like we were doing a batching of 4 sequence, I need to multiply by 4 for effective tokens per second, which will come somewhere around 640 620 tokens per second. So similarly, when 2 instances were run in one A100, then the effective tokens per second, right, will come down for each sequence. So that will be somewhere around 87 to 88 tokens per second. Since batching is involved, I'll multiply by 4, and also since 2 instances were there, so I'll multiply by 2. So this will be somewhere little bit like some 4 to 5 tokens, little bit more than the actual tokens. But when you run 2 instances, the GPU will be 100% full. And similar for L4, when one instance was run in L4, we were getting 57 to 58 tokens per second, and that's why I'm multiplying by 4 because of batch size 4. And this all experiment were done in FP16, not in date or anything. And similar to that, one instance in 200, which is tensor parallelism 2, when we run, we were also getting similar 162 to 164 tokens per second in the same node, not on our across the node. So this is the tokens per second. Now we need to understand the model's details. Like this is a Qwen model, and library that we are using is VLLM, which supports batching and model splitting as well. And if for our experiments, we are keeping only 4 as the batch size. So for this load testing scenario, I'll discuss later. And let's understand the hardwares that we have. I have already discussed this number of hardwares in the previous video, but again I'll reiterate here. So we had 5 different nodes, and in that node 1 was having 100, and node 2 was having node 2 and node 7 was having 2 800s. Node 4 was having 4 L4s, and node 9 was having 4 800s. So now we need to calculate, okay, we have this many instances, right? So how much instances we'll be creating. So that's that we need to calculate. So to calculate that, we need to understand the RAM usage per instance. So one instance takes around 4.5 GB of RAM. So multiple instances can be run on 800 because we have 80 GB of RAM. But problem is GPU utility is not enough to run many instances. So we have to restrict with 2 instances only per 800. And TP is not required as it is small. The models are very small. We don't require model splitting at all. So TP is not going to be considered here. And one instance can be run on only one L4. So only 4 to 5 GB it will take in, though it has a 22 GB, but GPU utility is reaching 88 to 95%. So we'll restrict with one instance in one GPU for L4. So if you calculate number of instances, right? So since node 1 has 1 800, I'll run 2 instances. Node 4 and node 7 has 2 800s, I'll run 4 instance. Node 9 has 4 800, so I'll run 8 instance, and node 4 has 4 L4, so I'll run 1 instance per GPU. So totally that will sum up to 22 replicas. So you need to in your allocation.json, this is my blocks Qwen3 1.7B VLLM allocation.json. You have to change your max replicas to 22, minimum replicas to 1. So post doing that change, again to calculate the throughput, so you need to run with the number of requests, right? So for that, to do that calculation, so you need to understand how much tokens each instances will provide. So 2 instances on node 1, 2 instances on node 1, 4 is the batch size, and effective tokens per second you are getting is 87 to 88. So this will sum up to 696, similar to 2 800s, and 2 800s will give somewhere around 132 to 1392 tokens to 1408, and 4 800s will give you somewhere around 2784 to 2816, and 4 L4s will give 912 to 928 tokens. So if you sum it up, so you will get somewhere around 7.1k to 7.2k tokens per second. So now let's divide this by 256 so that we have the 256 as a max tokens per sequence. So it will be somewhere around 28 to 28.3 requests per second is an ideal number. So because here this is just about the output tokens only, we have not considered how many tokens are prompt evaluation time we call. So how much token it takes to evaluate the prompt, and queues, latencies, AIOS latency, nothing is considered here. It is just about the output tokens only. So with that, we'll get a 28 requests per second. This is an ideal scenario. So I will not go to the ideal scenario because like a lot of other things are involved. So I'll start with 15 requests per second. So for my 15 requests per second, in Magistral, we were doing it with 2 requests per second when this number was somewhere around 3.5 to 3.8 was the request per second. So we were considering 2. So here also similarly, little more than 50% I'll consider, which is 15 requests per second. And for this, I require 200 users. So 200 users I'll create with the 2 sessions each. So if 15 requests per second, let me calculate how many requests I'm sending per hour. So which is like into 3600. This will end up with 54,000 requests per hour. So in previous experiment, maybe that number is yes, this number was 7,200 requests per hour in the magistral experiment. Here it is 54 requests per hour, 54,000 requests per hour. So, so for 54,000 requests per hour for 200s, which is equivalent to 270 requests per user, because we have 200 users. And to calculate, since we have two sessions, 270 divided by 2, which is 135. So this is the number that we need to dump in our conf.yaml. So if you go to conf.yaml, so you have to play that 135 here, and sessions per block is 2. So sorry, it is sessions per user, it is 2, and 135 requests per hour per session is what we are going to start. And so this is the usage pattern. So I'll come back to the usage pattern a little bit. So user per hour is 200. So with that, we'll be doing our experiments, and post doing the experiment, we have got certain results, which is what I'm going to show you right now. Let me directly show you the output of the request response timings. So so this was the response time. So you can see here it is varying from 10 seconds to 200 odd seconds. So around this time, so this experiment was run from 22 hours to 6 hours in the morning, and during this time alone, you can see that there is an increase in the so there is an increase in the time response time. So it is because it goes with your conf.yaml. So as you can see, around the 23 hours, so this number was 40% of the full 15 requests per second, whereas as soon as 12 o'clock is crossed, so it will be somewhere around 97% of the 15 requests per second. So because of this, what happens is, when it was in 11 o'clock to 12 o'clock, right, so number of instances could have been very less, maybe it's 8 or 10 or 12, something like that. So suddenly at 12 o'clock, it has to increase to around 21, 22 instances. But as you can see in our allocation.json, we have an average cooldown seconds as 120. So every 2 minutes only it can generate a one instance. That's what we have controlled with. So you can maybe if we reduce this, right, so definitely this response time also will come down, because you are after 12 o'clock, you are starting more and more requests per second you are trying to hit with the instances, but all instances are not capable of handling that much request. So some more instances are needed, but every 2 minutes only we are creating one instance. So because of that, this was the pattern. So response time was slowly increasing, but once somewhere around 22 instances were created, right, so slowly again it will come down. So because now all instances are available, and it can give you a responses. So the load balancer will take care of shuffling those sessions IDs to all the instances. So you will get a faster response. Again, now it will come down to the normal 50, 40 or so seconds or so. So in that time interval, if you see 22 hours to 6 hours, so total number of requests were sent is somewhere around 328K. In that request, let us see how much of failures. Failures here is mainly because of timeout. So what is a timeout is 1200 seconds is a timeout. So if a response is not received within that, so I'm calling it as a failure. So if I check the number of failures, right, so it has gone somewhere around 104 only in that duration, 22 to 6 o'clock duration. So which is minimal, but though my client code has again retry attempts, right, it will try to retry. So definitely those requests would have been got a responses, but is the first time failure only I'm noting down. So so this is about the request response and failures. So if I go to the Grafana dashboard, so just to show you the average queue length and all. So this is the summed queue length for Qwen and Sloth 3.17B model. So around at, yeah, it's also having similar pattern around at 12 o'clock, right? So you had the queue length is increasing because not many instances were there, and slowly as soon as number of instances goes to, let me say, this is the instance count. So slowly the instance counts will start increasing around at maybe at 32 1232 around, you got all the 22 instances. So from 1232 onwards, slowly it started reducing. So that's why whenever lesser instances are there, you will see an increase. So if you reduce that 128 to maybe a 30-second, right? So you will not see this much of a higher queue length, because instance will spin up faster, and they are available for processing. Yeah, again, the instance counts will go up and down because of again the configure YAML, because you are again reducing the at 1 o'clock you are reducing the number of requests you are giving to the instances. Again at 2 o'clock you are reducing, again at 3 o'clock also I'm increasing it to 97%. So again at 3 o'clock, right? So you will see a smaller increase in queue length. So that's the pattern you will see. So yeah, this is about the instance count and the average queue length, and also the tokens, total tokens summed up, right? So from all the instances, it will come somewhere around 7,000 to 8,000 requests, sorry, tokens per second is what you will see. So this is about the Grafana dashboard, where you have a block metrics aggregated. So you can use probably the So you can use this particular dashboard VLLM unsloth Qwen3 1.7 to create this dashboard. This dashboard.json is for the magistral model, because the model name is hard coded in this JSON file. So if you are using it in Grafana, you use this particular JSON file. So so that's it for this video. So you have seen a higher number of requests per second was sent. Our platform is able to handle that with very minimal number of failures. And the let's say whenever the number of instances are increasing or reducing, right? So I mean increasing, during that time only you would see certain failures, because the input is very high, and at that time you are not many instances for that, so you might get a more timeout request, because the queue is getting increased very high, and you might get a more timeout request. That's it for the video. In this video, we showed you how to strategize for a smaller model for block scaling and load testing. And in the part 1, we showed you for a mid-size model. So you can do similar experiment for the larger model as well. So thanks for watching the video, and don't forget to subscribe the video.